All right. Hey everybody. Thanks for watching. Today we're covering the Brouwer fixed point theorem. At first in dimension 2, and then we will be talking about the Borsuk-Ulam theorem in dimension 2. Um, and then we're gonna see how far we get. I think we'll probably get up to maybe including induced homomorphisms. Um, it would be really nice if we could finish off the chapter today. Um, or not the chapter, the section. Boy, it would be cool if we could finish 1.1. We'll start with a theorem, and this theorem is theorem 1.9, says that every continuous map H from the 2-disk to the 2-disk has a fixed point, i.e. x in D2 with h of x equal to x. Yeah. So, standard notation here is that Dn is the closed unit disk in Rn. All vectors x of length modulus less than or equal to 1. And then the boundary of Dn is the unit sphere Sn minus 1, which in this case is a circle. And so this is, I'll just mark this as Brouwer. How does one spell that? Brouwer fixed point theorem in Dim 2. And the proof is actually fairly short. So assume, for contradiction, that h of x does not equal x for all x in the 2-disk. Then we can define a map R from the 2-disk to its boundary. And I'll just go ahead and start by saying that this notation means boundary. With R of x mapping things kind of to their spot on the boundary. So pictorially, this looks like if we have our center point, or I guess if we start with x, we have h of x kind of arbitrarily over here, and then we map array as a straight line from h of x through x onto the boundary. So this is kind of like the thing that happens first is we pick x, then we say h of x is not a fixed point, and then we map it to r of x, which is kind of the more interesting thing here. So it's clear that r is a continuous function, since small perturbations of x produce small perturbations of h of x, meaning that if we move r of x to be like here, then we have to have a straight ray that is the same distance away, and that this angle is preserved. And so it's not explicit that this is over a metric space. I don't think it needs to be. But I think that it is a metrizable space for sure. So hence also small perturbations of the ray between these 2 points corresponds, yeah. So the crucial property of R besides continuity is that note, if X is in the boundary of the 2-disk, then R of X is equal to X. And so R is a retraction of the 2-disk onto onto the boundary of the 2-disk, which is the 1 sphere. And then the contradiction that we're looking for is that there does not exist such a retraction. So to accomplish this, we will let F naught be any loop in S1, which is again the boundary of D2. Well, in the 2-disk, there is a homotopy of F naught to a constant loop. Like we could accomplish this with the linear homotopy, e.g. straight line homotopy. Where X naught is the base point. Of F naught. Since the retraction R is the identity map on the 1 sphere around the circle, the composition R of the straight line homotopy is a homotopy in S1 from R of F naught to F naught, which is the constant loop at the base point. But then this is a contradiction, since this would mean that pi 1 of S1 is the trivial group, which we know to be false. And we've just claimed well, I mean, this is exactly what we've claimed, and we've shown that it's not. That pi 1 of S1 is 0. So is this a clear proof and a clear explanation of the proof?
Yeah, I think so. I think this is a pretty good following of what Hatcher has done here.
Okay, cool. Yeah, so this theorem was first proved by Brouwer around 1910, one of the early triumphs of algebraic topology. Brouwer proved it for Dn, and we can obtain this this generalization in Corollary 2.11 in the chapter on homology. You can also use the higher homotopy group pi n. Brouwer's original proof used neither homology nor homotopy groups, which had not been invented at the time. Instead, it used the notion of degree for maps Sn to Sn, which we shall define in 2.2 using homology, but which Brouwer defined more directly in geometric terms. It's kind of funny, my parents ask me "Oh, are you making new math yet?" And I keep having to answer, "No, but the new math that I'm learning is within the past 100 years of invention, so I'm getting pretty close."
Yeah, I feel like the same way is like whenever you explain it, it's like, yeah, new math is 100 years old.
Yeah, I mean it's really something like, and how much has just exploded in this last century or so.
Yeah.
Kind of sucks, right? Like I guess at some point like everything was cutting edge and those people thought that their work was never going to be used, but like there's so many classes now to get to the point where you're like learning the new math of 10 years ago, like it's almost a grad school level thing.
Right, right.
Yeah. Anyway, so these proofs are all arguments by contradiction, so they just show the existence of fixed points without giving any clue as to how to find one in explicit cases. Our proof of the fundamental theorem of algebra was similar in this regard. There exist other proofs of the Brouwer fixed point theorem that are somewhat more constructive. For example, the elegant and quite elementary proof by Sperner in 1928, which is explained very nicely in a second course on algebraic topology by Eigner and Ziegler. The techniques used to calculate pi1 of the circle can be applied to prove the Borsuk-Ulam theorem in dimension 2. So, theorem Borsuk-Ulam. For every continuous f from the 2-sphere to R2, there exist x and minus x, which are antipodal in the 2-sphere, with f of x is equal to f of minus x. It's really funny. There's this great lecture series that I started off last time talking about and kind of showing it a video of, but of this professor from, I think, Andrews College, teaching algebraic topology, and he has like a globe and he shows his students. He's like, yeah, so Borsuk-Ulam says that like if we can measure like temperature and wind speed at two antipodal points on a globe, there's at least one point on the globe where like antipodal points imply like the same temperature, let's say, same temperature and wind speed at two antipodal spots on the globe. And they give him just this horrible hard time about like every single possible way that you could disavow this in real life. Like, oh, well, what if it's not a continuous manifold? Like, what if we're not on a manifold? What if the Earth isn't perfectly round? What if? And he was like, guys, shut up. Anyway, I thought that was really beautiful. Um, yeah, so, let me prove this, right? Yeah, okay. So maybe that there's only one such pair of antipodal points. Borsuk-Ulam also holds for n-dimensional sphere to Rn, as we will show in proposition 2b6. The proof for n equals 1 is easy since the difference f of x minus f of minus x changes sign as x goes halfway around the circle, hence this difference must be 0 for some x. For n equals 2, the theorem is certainly less obvious. It's apparent, for example, that at every instant there must be a pair of antipodal points on the surface of the Earth having the same temperature and same barometric pressure. The theorem says in particular that there is no one-to-one continuous map from S2 to R2, so S2 is not homeomorphic to a subspace of R2. An intuitively obvious fact that is not easy to prove directly. Yeah. So likewise, we'll do a proof by contradiction. So assume contradiction. Define g from S2 to S1 by g of x. Nope, that's going to need more space. By g of x is equal to f of x minus f of minus x. divided by the absolute value of f of x minus f minus x. And this is, I gotta say, this is looking awfully familiar to when we proved the thing about the fundamental. This is looking awfully familiar to this. But I digress. I'm just kind of wondering if that's a trick. So then define a loop eta circling the equator of S2 contained in R3 by eta of S is equal to cosine 2 pi S and then sine 2 pi S and then 0. And let H be from the unit interval to S1 be the composed loop G eta. And I'm kind of wondering, so that doesn't seem like that'll work, but okay. Since g of minus x is equal to minus g of x, g of minus x, yeah, it's minus g of x. We have the relation, and this seems, so s plus 1/2 is equal to minus h of s for all s in the interval from 0 to 1/2. How the hell? So I get the nope, I don't get it. So it seems like eta gives us something in R3 that's definitely bounded. But then g of eta is something between 0 and 1 minus something between 0 and 1 divided by its absolute value. And I'm trying to think of a scenario in which case this is not plus or minus 1. I'm going to go to Desmos real quick and just test something real quick. So if f of x is like x squared, g of x is equal to f of x minus f of minus x divided by the absolute value of f of x minus f of minus x. it doesn't show up because it's division by 0. Yeah, it's just plus or minus 1. But what if like we have like e to the x? Still plus or minus 1. What if we have e to the minus x? It switches. So this is plus or minus 1 no matter what. Maybe x cubed e to the minus x plus 6. Nope, doesn't matter. Yeah, okay. So that's a thing. So g of x is always going to give us plus or minus 1. Oop. And so then h is plus or minus 1. If s is in 0 to 1/2, then this is the same thing as going to minus 1/2 to 0. I guess is maybe the implication here. And so then the unit interval is not wrapped from 0 to 1, but it's from minus 1/2 to 1/2. Does this make sense to you, Zach?
I'm trying to figure out why the g of minus x equaling minus g of x
Let
induces the
me
relation.
let me share my screen, because it'll help make some things clear, I
Okay.
think. Oops. Um, there we go, share screen. Yeah, so like we can type in kind of whatever we want,
Okay.
and end up getting this plus or minus 1 thing going on.
Okay.
And so then if we restrict, like if f of x really is this business of I guess cosine 2 pi x sine 2 pi x comma 0. Um, Maybe it'll work for this. Does that do this? Then like g of 1/2. I mean, we can do this piecewise, right? Like,
Yeah.
if we're just looking at cosine of 2 pi x. Um, then like g of 0 is 0 over 0. Wait, okay. Wait, so what if it's just cosine of x? I think that cosine is always a problem. Sine of x gives us plus or minus 1. 0 is similarly undefined. Um, yeah, so sine of 2 pi x definitely does give us this 1/2 thing. Right?
0, 1, 0, 1. Yeah. That makes sense.
That makes sense. The cosine bit, um, the cosine bit is 0 over 0. The sine bit is 0 over, so the sine bit is plus or minus 1/2.
1/2. Yeah.
Um, and then the 0 bit is also 0 over 0, and so
Oh, wait, is that why the relation is if you add a half, then you're basically moving on to the next whatever bit, and it's so it's negative.
yeah.
Okay, that makes much more
But
sense.
I'm
Okay.
wondering what the hell is up. So, like, with eta of s being this tuple cosine, sine, and 0,
Okay. Yeah.
it's undefined everywhere except in the second slot. Like, here, I'll screen share it. It'll make a little bit more sense. So, like this is pretty clearly 0 over 0. That is pretty clearly 0 over 0. This isn't. And
Hmm.
so h of s plus 1 half is equal to minus h of s. And I guess in the first and third slot, it doesn't matter?
That doesn't make much sense.
Um, maybe this is one of those things that will explain itself.
Sure. I guess we can like continue and see.
So, as we showed in the calculation of pi 1, we can lift h to a path. And so we'll let h tilde from I to r be a lift of h. Then h tilde of s plus 1 half is equal to minus h of s plus q over 2, where q is an odd integer, um, which depends on s. No, which what? This proof is so interesting.
Wait, so does Q depend on S or not?
Well,
Because
it says some odd integer q that might conceivably depend on s, but in
yeah,
fact q is independent of s by solving blah 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 blah. We see that q depends continuously on s.
yeah, okay, yeah, I'm just reading that too. All right, yeah. So we go from conceivably
So
depending,
this is either an issue of English grammar, the
yeah,
author's
or
understanding of English grammar, or this is just a really bad proof.
yeah, because we go from depending to independent to continuously depending.
Independent, dependent, continuously dependent.
It's H it's Q
Okay, what is
times
it trying to say here?
G. Yeah.
We're saying that we have this thing that switches back and forth between 1 and minus 1, and on the interval from 0 to 1 half, we get this relation, and that relation looks like an antipodalness. And what we're trying to show is that if we have a lift, then this thing Q is some scalar of a generator of pi 1 of the circle. And since it's odd, we don't do a full loop eventually. And so that h doesn't contract to the base point. And then H is supposed to be null homotopic because S1 is homeomorphic to the sphere. And so eta is clearly null homotopic. And so then H should be null homotopic. And so basically, as long as Q is odd, that's what matters. Okay, so cross out like 3 lines of that proof mentally. Q is an odd integer, which definitely depends on S, because it is the winding number of what interval we're in. And
I,
then basically, basically, H is equal, and this is an abusive notation that the author uses, so whatever. Um, H is equal to Q times A, where A is equal to pi 1 of S1. Um, and then since Q is odd, um, QA looks basically like if we fix our base point here, this is X naught, then we have it goes around like okay, that's not as obvious as I wanted it to be. It goes around like an odd Q over 2 number of times. And so we end up getting this antipodal thing. Um, so H isn't null homotopic because it doesn't contract back to the base point. Or rather, it isn't null homotopic on 0 to 1. But since G and eta are null homotopic, which I'll show in a second, and G composed with eta is null homotopic by assumption, we have a contradiction. So in terms of G being null homotopic, it literally just doesn't contract back to itself because we have at 0 it's inclusive at positive 1/2, but then at 1 it's inclusive at negative 1/2. And so it's like we can't identify the 2 points unless we make a special equivalence class for plus or minus 1. And then eta is null homotopic for reasons I'm not sure of, because it really seems like that would be null homotopic. Oh, it's because it is. Yeah, no, they're both null homotopic. And then the idea is that somehow this thing comes along. And I guess Q is really 1/2 minus S, right? 1/2 minus S times 2.
yeah, if you
One
can
half
like
minus S times 2.
yeah.
I don't know if that's true, because that isn't necessarily an integer. Q Oh, it can take on rational values, but we constrain it to integer values. And so even though it does depend on S continuously, it depends on rational variations around singular like integers.
Okay.
And since we fix it to be an integer, it's constant. So the lift at 1 is equal to the lift at 0 plus q. So like I'll just write this as deriving q. The lift at 1 is equal to the lift at 0 plus q is equal to the lift at 1/2 plus q over 2. Um, so this means I don't know. That's not a good argument. It would be good if they showed us how to derive q. This is not a good enough answer. Am I crazy? I'm gonna say dot 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 square. Maybe look this up in your own time. Um, because that's an unsatisfactory argument. We'll leave it at that. So, in any case, the point of Borsuk-Ulam is that continuous maps from the 2-sphere to R2 have antipodal points that encode the same information. And so, as a corollary, if S2 is equal to A1 union A2 union A3, where AI are closed in S2 under the induced topology, then at least one set must contain a pair of antipodal points. And so Hatcher starts by metrizing this. So let di from S2 to R measure distance to AI, i.e. di of x is equal to the infimum of y in AI of x minus y. This is continuous in the standard topologies, so we can apply. So since di is continuous, we can apply Borsuk-Ulam U to the map S2 to R2 by X to the tuple. Oops, my Apple battery is low. I almost charged it because I was like, I've been using it a lot, but we'll give it like 3 minutes. Basically, we get a tuple containing the distances of d1x and d2x, and we treat these as antipodal points, x and minus x. No, we find d1x and d1 of minus x, and then d2 of x and d2 of minus x. If either of these two distances is 0, then x and minus x both lie in the same set. On the other hand, if these distances from x and minus x to a1 and a2 are both strictly positive, then they must lie in the third one because they don't lie in any two of them. To see that the number 3 in this result is the best possible, consider a sphere inscribed in a tetrahedron. Okay. So it's like a pyramid. I don't know if you can see.
Yeah, I got
That?
you. Yeah, yeah,
Yeah.
yeah, yeah. It's like a double or two
Yeah.
pyramids like on top of each other in a circle inscribed.
Projecting the four faces of the tetrahedron radially, we obtain a cover of S2 by four closed sets, none of which contains a pair of antipodal points. But why 3? I get that you can't do it for this case of 4, but what makes 3 special? It really feels like he just kind of declined to prove that 3 was special to this. Um, this feels terribly hand wavy. Um, this is a very interesting distance metric, though. Um, okay, let me check my Apple Pencil battery settings. Apple Pencil. Okay, 20% should be fine. So we're sending x to d1 of x and d2 of x, and then using Borsuk-Ulam, then let d1 of x equal d1 of minus x, and d2 of x equal d2 of minus x. If either is 0, x and minus x are in AI. If both are 0, then x and minus x are in A3. That doesn't make sense. No, it's that if they're both strictly are greater than
Yeah,
0.
it's both positive. Yeah.
Um, okay, I mean, like, that makes a little bit more sense about why 3 works. It would seem that A1, A2, A3. Yeah, it is a partition of S2. Okay. Okay, yeah. I feel a little bit better about that. So assuming the higher dimensional version of Borsuk-Ulam, the same arguments show that Sn cannot be covered by n plus 1 closed sets without antipodal pairs of points, though it can be covered by n plus 2 such sets, as the higher dimensional analog of a tetrahedron shows. Even the case n equals 1 is somewhat interesting. If the circle is covered by 2 closed sets, one of them must contain a pair of antipodal points. This is, of course, false for non-closed sets, since the circle is the union of two disjoint half-open semicircles. The relation between the fundamental group of a product space and the fundamental group of its factors is as simple as one could wish. Did I skip a page? No? Did I? 33.
Nope.
Boy,
Nope,
that
that's
just
right.
leaps topics. Okay. Man, this has been a really thoroughly written book so far. This is feeling reminiscent of Arton's algebra book.
Yeah.
Um, okay. So pi 1 of x product y is isomorphic to pi 1 of x product pi 1 of y if x and y are path connected. Um, dude, if this somehow wraps back around to antipodal points, I will be amazed. It doesn't. The proof doesn't. What's even the point? There was just no trans. I think he like literally was like, "Here, I'm gonna put this at the end of a page and write filler stuff until the page ends, and
Let's
hopefully no
switch
one's gonna notice."
switch topics completely. I mean, I guess we are. Yeah. Okay.
I mean, like it's in the topic of the section, but
Yeah. Yeah.
no transition whatsoever. Okay. Um. All right. So a basic property of the product topology is that a map from Z into X product Y is continuous if and only if it factors through the unique things. So hence a loop based in the product space at X comma Y is a pair of loops in X and a pair of loops in Y. Um, so this is where I'm actually going to take the time to talk about the universal property of products, and then I'm going to show this in the category of topologies because this is something useful for like general knowledge. Um, so universal property of products and fiber products. So what it's talking about is this is a universal diagram for any category, meaning that if we have something um, like z factoring into x and y, if we have like a loop in z that we want to send just to x or just to y, it factors uniquely through the product. And so like if you think of all of the spaces in a category that you can put together and you want to send something like as a projection just into one of them, it technically factors through the product, you just forget everything, kind of going from here to here. And so this is the product. But then the co-product is this thing that reverses the arrows and says, okay, if we want to send stuff back to Z just from X, then it's going to factor straight through the disjoint union of X and Y. And so the idea is that like you can send stuff as an embedding X into Z, but you can identify it with all of its possible pairings of things and Y's as like disjoint copies of each other. Um, in the category of topologies, the coproduct is the same thing as disjoint union. So disjoint union, and they share notation, so like whatever. But then basically, as a property of like this stuff, if we spot like a loop in here that's in the product space of like X product Y, um, then it's just a copy of loops in Y and a copy of loops in X that factor into Z through the product. Um, and so then that's why the fundamental groups like have this notion going on together. Um, yeah. So as an example, I don't know if it's an example of this, but maybe it's just of oh, right. I was going to talk about fiber products. So fiber products are this really interesting construction, and I'm not entirely sure that algebraic topology uses them as much as algebraic geometry. But So a fibered product is this thing that we'll sometimes call the pullback. And so the fibered product through Z of x and y is if we have y here and if we have x here, then if we have maps alpha and beta into Z down here, then x fibered through Z of y is the set of all pairs x naught comma y naught in x product y, such that alpha of y naught is equal to beta of x naught in Z. So it's all of the stuff that agrees in Z. And so this is useful because it gives us kind of a way to like pull back agreeing things as a structure. And you can like, this becomes particularly relevant when we'll talk about homology and cohomology groups, because you can characterize a lot of things with pullbacks. And then like a push forward is kind of like a dualizing version of this. And that's, I think, definitely more used in algebraic geometry. But it's a very interesting construction, and it follows from the construction of the product, and it definitely works for like loops as well in terms of like pulling back minimal loops that agree in another space. It works very nicely. And that's kind of the undergirding of this proposition 1.12. So yeah, this other example, the torus. So by proposition, above we have an isomorphism pi 1 of S1, product S1 is isomorphic to Z product Z. And so under this isomorphism pair, for every pairing P and Q in Z product Z, we get a loop which winds around S1 P times and the other one S1 Q times which is equivalent to a torus wrapping of P plus Q times. And I'm pretty sure this is what we end up generalizing as the cup product in the section on homology. But I could be totally talking out of my ass there. Fair warning. So earlier in the last lecture, no, it looks very like the Borromine rings, but basically this results in what look like torus knots. So if we have a circle here and if we have a circle, no, that's not very helpful. I did not draw a square. Okay, man. Yeah, sure, that's fine, whatever. If we have like, I'm gonna try my best to draw this. Something like this, where like we identify this end and this end, and then this end and this end, and this end with this end, and this end with this end, in terms of going over and under. Then this is a torus knot. More generally, the n-dimensional torus, which is the product of n circles, has fundamental group isomorphic to the product of n copies of Z. So I don't actually know what the abbreviation for the torus is. So I'm just going to say that n torus, which is equal to which is equal to product of n circles has pi 1 of n torus isomorphic to Z to the n. Okay, cool. We're exactly halfway, and we have 3.5 pages, so that's pretty good. So induced homomorphisms. Any questions on this before we move on? Any of the product stuff, fibered product, torus knot.
No, I think I'm good. Yeah.
Cool. Yeah, I figured. But any questions, comments, concerns you think that would help anybody watching this? That might be a more
I
fruitful
mean,
question.
we didn't necessarily go over the proof for the proposition, but I mean, we don't have to. I don't think we did, right? Yeah.
Yeah, we didn't. I basically just said it follows by universal property of
Okay.
products.
Okay. Yeah, yeah. That's
Yeah.
good.
Um, and that is the proof that they go. Like, if you want a good example of the universal property of products, um, the proof is like an example in the category of topologies. So, um, yeah. So for induced homomorphisms, suppose phi from x to y takes base points in x to base points in y. Um, then phi induces phi star from the fundamental group on x to the fundamental group on y naught, defined by composing loops. By composing loops f from I to x based at x naught with phi, i.e. Phi star of f is equal to phi of f. This map is a well-defined one since a homotopy of loops yields a composed homotopy of loops. And then furthermore, we can verify homomorphism properties since this just comes out to be, so is a homomorphism by phi star of f g is equal to phi of f composed with g, which is equal to phi f phi g. Um, so two basic properties. of induced homomorphisms. Induced homomorphisms. One is that phi psi star is equal to phi star psi star for the composition x naught by phi to y naught to z naught. And then one star, which is like identity, is equal to 1 is equal to idx, induces 1 pi. The notation for identity map in this book kind of sucks, I gotta say. That's been like my main complaint so far. But induces an identity map from one fundamental group to itself. So the first of these follows from the fact that composition of maps is associative. The second is obvious that these two properties of it literally says the second is obvious. These two properties of induced homomorphisms are what makes the fundamental group a functor. Yeah, this is true. The formal definition of a functor requires introduction of certain other preliminary concepts. We'll talk about this in 2.3. It carries over objects and morphisms from one category to another. It's associative and transitive. If phi is a homeomorphism with inverse, then phi star is an isomorphism with inverse. Yeah, I guess that's a good remark. So if phi is a homeo, then I guess with inverse psi, then phi star is an isomorphism with inverse psi star. And so this fact actually becomes very useful for the calculation of fundamental groups of higher dimensional spheres. So proposition is that pi 1 of Sn is equal to 0 if n is greater than or equal to 2. Ooh, I really wonder if that has to do with Fermat's last theorem. That really feels like that would have to do with Fermat's last theorem. Because, I don't know, you don't really see the n greater than or equal to 2 show up that often. I'm just going to put a little bookmark in here because I'm working through that paper over break. Fermat's last theorem? Okay. I don't know. Maybe I'm just wrong, but I would be interested to see. So proving this, so let f be a loop in S to the n at x naught if the image of f is disjoint from x in Sn not equal to x naught, then f is null homotopic since S to the n minus x is homeomorphic to Rn. um, which is simply connected. Let's break that down. So Sn minus x is homeomorphic to Rn. Because I guess minus x would be the infinity point. If we wanted to turn... Am I logicking correctly here, Zach? Like, if we remove 1 point from Sn, then it's like removing the infinity point from Sn,
Yeah, I think
and
that's
that
right.
gives us the home. Yeah, okay.
Yeah.
Um,
I think we did something similar in
yeah,
class, right? Yeah,
yeah. We did like a good mix of this stuff, so it's like mostly familiar.
right.
Um, so it will suffice to homotope F to be non-surjective. Um, so we can homotope F to be non-surjective. To do this, we will look at a small open ball. Let B open in Sn. Um, at x not equal to x naught. Um, and see the number of times that F passes through X and leaves. C number of times F enters B, goes through X, leaves B. Um, and then that number is finite. And each of these portions of F can be pushed off X without changing the rest of F. Um, so it seems like if we have this circle and we have this base point x naught, or we have x, and like the idea is we can just remove x and like blow up everything around it, maybe. So this construction is F inverse of the ball is open in the open set 0, 1. Okay, that's like really abusive notation, but whatever. Um, so F inverse of B is the union of a bunch of AI BI intervals in Rn. Oh, and it's the disjoint union. I don't think that matters here. Um, then F inverse of X is compact and closed in the union of finitely many of them. And so consider one of the intervals AI, BI meeting f of x. Consider AI, BI intersect f inverse of x. Then let fi be the restriction of f to AI, BI. Which is in the closure of B. And then f of AI and f of BI are in the boundary of B closure. No, just in the boundary of B, which is in B closure, but whatever. So then if n is greater than or equal to 2, let gi be a path from f of AI to, just as an abusive notation, I'm making a squiggly arrow here. So f of AI to f of BI in the closure without x. So we could pick it to lie in the boundary of B, which is a sphere of dimension n-1, and thus path connected. Since the closure of B is homeomorphic to a convex set in Rn, Fi is homotopic to Gi. So since B closure is homeomorphic to a convex set in Rn, which is convex, and so simply path connected. Then Fi is homotopic to Gi. Which is then eventually homotopic to F by repeating this process for each of the intervals. So G, which is the branch union of a bunch of these GIs, on basically the union of equivalence classes of open sets UI, GI, I, and I, where we can glue things on intersections of open subsets. Then G is homotopic to F. And G of the unit interval is disjoint from X. And so the idea is that pi 1 of Sn is equal to idx which is trivial if n is greater than or equal to 2. Okay, did I hit everything? Is that satisfactory?
see here.
I added some explanation where I felt like he just kind of jumped a little bit.
Mm.
Like this section here about gluing the GIs together. He doesn't actually give the condition for gluing them together.
Gotcha. Oh, yeah, I see what you're saying. Okay.
Um, and fun fact, that's an algebraic geometry thing that we'll get to soon. Um, yeah.
Yeah, I think you got everything. Yeah.
Okay. And does it like did it make sense conclusion wise? Like,
Um, well, okay, so I'm kind of um I got everything down. It's just when we go from, let's see here. Oh, okay, I see.
yeah.
Oh,
But we could just as equivalently do like, and then what we end up doing is we patch together like the least singular path.
oh, okay. Yeah, I have the image in the book. That helps.
Yeah.
Okay.
And
Yeah.
so basically, like the construction that I added does this where we cut out all of the singularities at like each of these cuspoidal points.
Gotcha. Okay.
And then we're just left with a smooth curve that F is homotopic to. And then we glue it together to get G.
Oh, okay. Fi. Okay.
And it
Yeah.
doesn't go around X.
Yeah. Yeah. Yeah.
But then this can be contracted to the identity map on X naught by straight line homotopy.
Okay. Yeah.
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 Yeah. And really like that's the whole proof. I feel like there's a lot of notation going on for that. One moment. Okay, this is actually really cool. I this is kind of separate. So I started making like math art for Christmas for people because I thought it was like, you know, like a thoughtful thing and but there's like I started making like homotopy art and like experimenting with it and they just came in from Staples. And so I'll show you I gotta unzoom so you'll have to excuse my messy room. But like it's pretty cool. I don't know how well it's showing up.
Let's see. Oh, okay. Yeah, I see it.
Yeah, and so it's
Nice.
like a thing I made in Desmos where it's like a homotopy thing where you just mess around at the interval of t.
Huh.
Anyway, it looks really good in real life. So, all right, now let me reblur this so that you can see anything. There we go. Okay. Um, cool. So of an application of this is that okay, there's an example and then there's okay. Example let X in Rn then Rn minus X is homeomorphic to Sn minus 1 times R So by the product thing, pi 1 of Rn minus x is isomorphic to pi 1 Sn minus 1 cross pi 1 of R. So pi 1 of Rn minus x is z for n equals 2, 0, for n greater than 2. And then an application of this is R2 is not homeomorphic to Rn for n not equal to 2. And like, duh? Like, okay. I guess really the theorem that's going on here is that Rn is not homeomorphic to Rm if and only if n is not equal to m. So I don't know. Okay, induced homomorphisms allow relations between spaces to be transformed into relations between their fundamental groups. So like fundamental groups are kind of the invariant that we're looking for on a lot of these spaces. So proposition 1.17, if X retracts onto a subspace A, then the homomorphism I star from pi 1 A comma X naught to pi 1 of X comma X naught induced by the inclusion I from A into X is injective. Then if A is a deformation retract of X, then I star is an iso, but really that shows surjectivity. So yeah, this proof is really small. Do you want me to do it? It's like a 2-line thing. I think it's pretty clear from definition.
Yeah, I don't think we need to really go through it. I mean,
Okay.
yeah.
So this gives another way of seeing that S1 is not a retract of D2, which is the Brouwer fixed point theorem, since the inclusion-induced map from pi 1 of S1 to pi 1 of D2 is a homomorphism from Z to 0, which cannot be injective. The exact group theoretic analog of a retraction is a homomorphism rho of a group G onto a subgroup H that restricts rho to the identity on H. So in the notation above, if we identify pi 1 of A with its image I star, then R star is such a homomorphism from the fundamental group on X onto the subgroup of the fundamental group of A. The existence of a retracting homomorphism is quite a strong condition on a subgroup H. If H is normal, it implies that G is the direct product of H and the kernel of rho. If H is not normal, then G is the semi-direct product of H and the kernel of rho. And I don't think that that is that important, but it is interesting. Recall from chapter 0 the definition of a homotopy as a family of maps such that all of the homotopy maps between are continuous. If such a homotopy family takes a subspace to a subspace, then we speak of a homotopy of maps of pairs, in particular a base point preserving homotopy is the case that the two homotopies between spaces are the same. So if they end up having the same family in both spaces, then it's a base point preserving homotopy. Another basic property of induced homomorphisms is invariance under base point preserving homotopy. So I guess phi sub t of x to x naught to y naught is a base point preserving homotopy if and only if phi t of x naught is equal to y naught for all t. Proposition if phi of t is a base point preserving homotopy, then phi evaluated at 0 star is equal to phi evaluated at 1 star. And short proof is that phi 0 of f is equal to phi 0 f, which is equal to phi 1 f, which is equal to phi 1 star f. And then this one comes from this condition. There was a notion of homotopy equivalence for spaces with base points. This is formally morphisms in the category of homotopy spaces. So x comma x naught is homotopy equivalent to y naught if there exists phi from x naught to y naught and psi from y naught to x naught with phi psi is equal to 1, psi phi is equal to 1 by maps fixing base points. Likewise, these are inverse isomorphisms between fundamental groups when we think of the star. So phi star, psi star are inverse isos of pi 1. Yeah, like this is not that crazy of a thing, I feel like, but for homotopy equivalences, since we don't have to like care about the base point as long as we're working in a connected domain, if phi x to y is a homotopy equivalence, then the induced homomorphism phi star from pi 1 of x naught to pi 1 of y naught. Nope. Phi of x naught, there we go, is an iso for every x naught in x. To prove this, we need a lemma, so we're going to put the lemma first. So if phi t x to y is A homotopy equivalence. Nope, is a homotopy. I read the wrong thing. The homotopy and H is a path phi t x naught formed by images of a base point then phi naught star is equal to beta h phi 1 star, where pi 1 of x to x naught goes by phi 1 star, pi 1 y, phi 1 x naught, phi naught star, pi 1 y, phi naught x naught, and then beta h. So basically it commutes. And beta h is the map that commutes, and it commutes to the base point. And then the proof is just by diagram chasing, basically. So to prove the above proposition, that the induced homomorphism is an isomorphism for every base point, proof of proposition, let psi from y to x be a homotopy inverse for phi with phi psi equal 1 and psi phi equal 1. Then pi 1 of x naught goes by phi star to pi 1 y of phi x naught goes by psi star to pi 1 of x comma phi of psi phi x naught, which goes by phi star to y psi phi psi. No, wait. Phi psi phi. Excellent. This feels like a tongue twister game. And then the idea is that this doesn't lose anything because these are like mutual inverses. So this goes to 1. And then since this goes to 1, this is just the first thing. And that's a group isomorphism. And then this is exactly beta h. So is that clear the way I've presented that?
Yep. I mean, it's pretty straightforward, I think.
Yeah, it's a pretty straightforward one. It's like, ooh, we have a category with associated maps. That's how it works. Yeah. Okay, cool. Well, then I don't have anything else prepared. Next time we'll pick up with Van Kampen's theorem. And I'm hoping to actually get through that whole section next time.
All right.
Um, and then yeah, cool. All
Do you
right, see
know
you.
of? Oh yeah. Just really
Let
quickly.
me
Do you
let me
know?
stop the recording
Oh
and
yeah, yeah,
then.
yeah, yeah.
Mm.